The invertible matrix theorem. Let A be an n by n matrix, then the following statements are each equivalent to the statement that A is an invertible matrix. Okay, that's here in fact in A. So A is an invertible matrix if and only if, all that means, if and only if A is row equivalent to the n by n identity matrix. So if this is true, then this is true. Or if somehow you find number 2 true, A is, you have a matrix A and you did the row reduction and you got n by n identity matrix. Identity means 1, 0, 0, 0, 1, etc. That means A is an invertible matrix. Okay, so all of these are equivalent. So if you have A has n pivot positions, if you row reduce and got n pivot positions, it does not mention whether that's row or column. In fact, it works in both directions. So if we have n pivot positions in row or also in column, if you have that, that means A is an invertible. That means determinant A is non-zero. In the same way, A has n pivot positions is same as the equation Ax equals 0 has only the trivial solution. Trivial solution means Ax is all zeros. Only the trivial solution. So these four are equivalent. So if this is 3 is true, then 4 is true, 2 is true, 1 is true. All the statements are same. I mean, they are equivalent. So you can read more and more. The columns of the matrix A form a linearly independent set. See? And the columns, not rows, columns. If A has n pivot positions in columns, or A is an invertible matrix, then the columns of A form a linearly independent set. The linear transformation is 1 to 1. So this mapping means we have domain here, range, code, here is Rn, here is Rn, because A is an n by n matrix. So A maps Rn to Rn, and they write here x to Ax. So we, in short, we write x vector is being mapped to Ax. Okay, Ax is mapped to Ax. This is 1 to 1. So like this, 1 to 1. If we have the linear transformation 1 to 1, that this is true when A is an invertible matrix or A has n pivot positions. All these statements are equivalent. The equation Ax equals B has at least one solution for each B in Rn. That means for each B in Rn, there is one, at least one solution. Means the codomain is same as range. When we have whole thing is codomain and everything is mapped, this map part is range. But if A is an invertible, then this range will be same as codomain. That's what it says in number 7. Ax equals B has at least one solution for each B in Rn. And this is equivalent to the columns of A span Rn. Okay, so if you look at the columns of A, these columns are columns of A span Rn. That means any vector in Rn is a linear combination of the columns of A. The linear transformation, this transformation maps onto. In fact, this is 1 to 1. When A is an invertible matrix, this mapping will be 1 to 1. So 1 to 1. And onto means everything is covered. Okay, everything is covered. That's what here in 7 as well. And there is an n by n matrix C such that C times A equals I. So it's pretty much like the inverse from left. and also a times d equals I, inverse from right side, and in this case C and D will be same. Okay, and A transpose is an invertible matrix as well. When A is an invertible, so is its transpose. The columns of A form a basis for Rn. They span Rn, okay, and we got n columns, so the dimension match, so they become basis. Basis means linearly independent and span, two things we have here, and they are linearly independent somewhere. So when A is an invertible matrix, then this everything is here, every single statement is equivalent to each other. Column of A, the column space of A will be the whole Rn. Okay, this is column space of A, and dimension of column space is n. There will be pivot in each column. Rank A is n. We know the rank. Rank is dimension of column space A, or rank is dimension of row space. Okay, we'll see that in next section. Rank of A is n, and null space of A, null space here, that will be just a single set, single element, 0. Null space, and dimension of null space we call 0. The dimension is 0. So these 18 statements are equivalent to each other.